Hi, my name is Sohan Paul. This is Physics 2211 BlackHole Lab. The purpose of this lab was to observe and analyze an object's rotational motion due to gravity interaction from a black hole. The lab was completely simulated in GlowScript because GlowScript allows for controlled repetition of rotational motion with massive objects. I used Newton's second law to determine the change in velocity from a net force acting on an object, and then used the velocity update law to determine the change in position. Additionally, the overall gravitational force was used to calculate net force on an object rotating or circling or orbiting an extremely massive object such as a black hole given to two masses, or we use this to determine the mass of the black hole. Additionally, we could track momentum or changes in momentum to determine the overall net force, since the overall change in momentum over time is equal to the net force. Part one of the lab, the starting conditions were that it started at time t equals 0, and then the ship black hole system was monitored over 1 day or 86,400 seconds. We assumed there was only gravitational force acting within the system, and there were no external forces on the system. In the ship planet black hole system in part 2, uh, the black hole was again located at the origin, but the planet was located 1 e to the 10 to the right of the origin. And then we also assumed there were no external forces on the ship planet black hole system, and only things acting between them was gravity. To the left, you can see the code I used for part 1 of the lab. Overall, we continuously updated a list with final initial velocities of the star around the black hole, and then we extracted two initial and final velocities and subtracted them to find the change in velocity. And then using the change in velocity over time, we could find the change in momentum over time, since momentum is simply mass times velocity. The change in momentum over time represented the overall net force, and then if there was any change in magnitude of the momentum, we knew there was a we knew there was a force acting in the parallel direction. Additionally, since the net force equals the perpendicular and the parallel components added together, we could subtract the parallel component from the net force to find the perpendicular component. To the right is the code I used for the second part of my lab. As you could see, we used the overall gravitational law, or law of gravitation, to find the force of gravity on the planet from the black hole and from the ship. And then if we added these two gravitational forces together, we got the net force on the planet. And then using the net force on the planet, we can use Newton's second law to continuously update its position using Newton's second law and then the velocity update law. Here are the results of my lab. Basically, I rearranged the overall gravitational force law to continuously calculate the mass of the black hole at different points along the trajectory. After collecting around 435 of these data points, I averaged them out to find the average mass of the black hole to be 1.78 to e to the 34th. For part 2, as you can see, I estimated the ship speed to be negative 3 e to the 7 in the x direction, or going to the left at that direction, and 0.64 e to the 7 going up in the y component of velocity for the ship to basically slingshot around the black hole, get close enough along the black hole, and have a high enough velocity to escape the gravitational pull of the planet, and still get close to the black hole and basically circle around it. We are asked how net force and its parallel and perpendicular components compare to the change in momentum and its parallel and perpendicular components. Well, according to Newton's second law, if the force is the cause, then the change of velocity or momentum is the effect. So while a net force is the interaction between objects, the rate of change of momentum is the observable vector that we can measure. Essentially, in part 1 of our lab, we tracked the star's velocity and thus could track the initial and final momentum for each delta t. And then we could calculate the change of momentum over time. This change of momentum is the quantity that represents the net force acting on the object over time. Some errors of the lab were the parallel and perpendicular components of my net force do not add up to the actual net force. There may have been some significant error or variance in the calculation of my net force, which have caused a lot of variance in the calculation of my black hole mass. Additionally, special relativity says that as an object moves arbitrarily closer to the speed of light, which our ship was, its observed mass which would increase, which was not taken into account. We're asked what initial velocity would our spaceship need to have in order to enter into some sort of orbit around the black hole. Well, if it was orbiting around the black hole, its centripetal force would be a factor of not only the gravitational force from the black hole on the ship, but also the gravitational force on the ship from the planet. Um, but at the same time, the velocity would have to be high enough to escape the planet's gravitational pull, and I estimate this to be negative 2.5 e to the 7 in the x direction and 1.2 e to the 7 in the y direction. In rotational motion, the net force on an object can be broken down into its parallel and perpendicular components. Parallel components decide if there is a change in the magnitudes of these components change over time, such as the magnitude and momentum over time, and perpendicular components decide if there's a change in direction over time. The combination of these two components can be used to describe the change in motion.